Hello, I'm Dr. Bradley Elisea, and I'm back with part 3 of breaking constraints, imposing constraints. So in this part, we're going to talk a little bit more about linking a lot of what we were talking about in parts 1 and 2 to cognition and cognitive systems. So we'll talk a little bit about energy and information in the context of sensorimotor feedback loops. And we'll be talking a lot about sensorimotor performance and some of the equations around that. So a very simple sort of representation of sensory motor coordination and sort of hitting a target that you see in the distance. So it's motor control and some of the sensory aspects of that. But we'll also get into this equation, which is Fitt's law. And it not only has connections to sort of the coordination of movement and motor control, but also information theory as well. So Fitt's law is a predictive model of human movement. It predicts that the time required to move to a target area, which we can define as something with a width, it's like a target, we saw on the first slide there with a dartboard with little zones that you have to hit, or it could be something like dropping something into a bin of a certain size, reaching out and dropping something into a bin. So something has a width, a target has a width, and then the distance to the target is also important. So the target also has a distance to destination. So you're reaching ideally from maybe your chest or maybe the side of your arms resting at your side, and you reach out and you hit the target. And there's a distance, but there's also a width. So we see that this equation is ID, which is the index of difficulty. That equals log 2, which is, of course, bits. And then this other part of the equation here, d over w plus 1. Now we'll get into what d and w mean in a minute, but you can see that we're going to turn it into a bit rate of some type. So the log 2 will be bit rate because you're going to take that proportion of distance and width and turn it into a log 2 transform, which is a bit. So, we think about this a little bit. Fitt's law really describes the ability for you to keep your arm straight going towards a target and being accurate in hitting the target. So if I have my arm at my side and I say, I want to reach out to the target and hit the target, sometimes that's a very easy task. Sometimes if it's a very short distance and the target is very wide, it's very easy to do. If the target is very narrow, maybe it's like a thin line, then it's a lot harder to hit. And the farther the distance my arm has to travel, the harder it is to hit. Because you have to form a trajectory with your arm, and your arm makes what they call a ballistic movement, which means that you can't easily alter it. You have to move your arm towards the target, and you have to know kind of what that sort of movement should look like before you initiate the movement towards the target. If you're off in that prediction, then you have to adjust your movement sort of towards the end of the ballistic movement. So that means that you're going to have a trade-off between the amount of time it takes you to hit your target and the amount of adjustments you need to make to the end of that ballistic movement. So I don't have any graphics for that here. Basically, it's like making a big arc with your arm, and then towards the end, just kind of adjusting your arm towards the target so that you can hit it. And of course, that adjustment has a cost in time. So we're going to talk about time. We don't talk about that explicitly here, but we're going to talk about it in a few slides. So ID is the index of difficulty. D is the distance to target, and we can think of that as the signal. So this is the signal where we have distance to target. We know that what we need to put into that signal to make it effective. And then the width of target could be called noise, because if the target is wide, there's very little noise. And if we make our ballistic movement, no matter what it looks like, if that signal is weak, but there's no noise, then it's sufficient for information processing. And of course, it gives us a higher bit rate. However, if the width is very narrow, the amount of noise is higher because you have, many potential movements. It's hard to hit exactly the right target. And that signal, if it's weak and if it's embedded in a lot of noise, you're not going to hit your target. So, there are other factors here that we're not going to account for. But in Fitts law terms, this is what we call the information of a sensorimotor movement. So, so we can think of the distance as signal and the width as noise. And so we can see that if you're throwing a dart at a dartboard and you hit the center circle, then you win that game. But that requires you to have a target of some size so that it's tolerant to error, some sort of error rate, which is the width of the target. So if that target were just a point, the tolerance would be very low. If that target were just the entire dartboard, the tolerance for error would be much higher for noise. And so you can have a lot of noise depending on the distance from the target. If the target is far away, you can have a lot of noise. But if you're tolerant to that noise, then it doesn't matter so much you hit the target. So in summary, D, or distance, is the signal. And we define our signal as the availability of the target, given the amount of time available and the accuracy of the controller. So in your arm movement, you're the controller, and you move your arm towards the target. Now you have to be accurate, so you have to have an initial prediction of where it is and make that ballistic movement. If you're not accurate, then you need to make adjustments. In the case of throwing a dart, you just miss your target and you lose. The other factor is the amount of time available. And so if you have to do this really quickly, if you're playing speed darts and you just keep throwing darts at a board without really making any sort of attempt to aim it, then you're going to be very much inaccurate. That accuracy will suffer because the amount of time you had available was very short. If you have more time, ostensibly you have more time to plan and predict, and that accuracy rate goes up. And this is something you can predict with Fitts law, at least in theory. So that's our D, and that's distance. Now W, which is the width of the target, is considered noise. We've talked about this already. This is given the signal relative to total bandwidth. So our bandwidth is the amount of, we kind of covered that with the index of difficulty, with the number of bits generated, and that's basically our bandwidth. But we need to have a high signal relative to the total bandwidth to overcome that noise. And so complex environments have a lot of W relative to D, which means that they have a lot of noise relative to the distance, or I guess you could think about it as the index of difficulty. So given like a complex environment, you have a lot of things around you, you have a lot of clutter, a lot of potential things to distract. Your target might be partially occluded by something like leaves or some other type of visual noise. The point is that that complex environment has a lot of noise relative to the distance or the index of difficulty of that movement. So if we fix that index of difficulty between a complex environment and an uncluttered or sparse environment, then the complex environment will have much more noise for a certain value of D. And so it follows that simple environments have less noise, or that the width is wider. And so I guess you can think of noise as almost the inverse of W, because if you have a wider target, if that W is larger in terms of a target width, that makes it easier. And if the target is narrower, then it makes it harder. But we think of W in general. You can think of it as the inverse, you can think of it as W. It doesn't really matter, it depends on how you apply this. And then well-learned tasks have less W, regardless of environmental complexity. So we have another factor here, which is learning and sort of the ability to know exactly how to make that movement. And you can think about this in terms of practicing darts. So if you throw your darts at the board, you learn the sort of movements that you need to make. You know what the best movements are, you know kind of your hand-eye coordination, and you learn that and you spend time training. And then when you're good at it, then if you go to do that task again, it's easier to do because you don't have to plan as much. It's already sort of encoded as a learned task. And so this is this type of procedural learning we call motor learning. And so motor learning is very important for this. So we don't have that in the Fitts law equation. We don't say, your learning rate is higher or lower. But we could add learning rate into that index of difficulty. And in fact, it would make it a more robust measure. But in any case, this is what we have in terms of theory. And so here's a graph showing the ID, or that index of difficulty, which we defined in the equation above. This is, of course, the equation of bandwidth, and then distance to target, which is just taking D out and plotting it out against the information. So we can see that we have this sort of curve with two ends, that kind of one that goes downward, one goes upward. And basically, if you have as the farther you get from the target, the higher the index of difficulty. They're negative values because we're just kind of normalizing it or something. But basically, this trend happens where you go, it's basically a linear trend, and then it's superlinear sort of at the end of this graph. It's sublinear at the beginning of the graph. So basically, as you get outward, it's harder and harder and harder, and then it becomes very hard at some point, at some distance. And so this is one way to represent this. Basically, the distance is a limiting factor on the bit rate on the bandwidth. And so then we can look at W and D and their relationship. So if W equals D, so we're looking at W here, and then we're also looking at D. So we're looking at D as distance to target, but we're asking the question, if noise is equal to the distance, then your index of difficulty is around 1. So we can see here there's an intersection of this function with the intercept with 0 on the ID path, and then we have it's about a 55 distance to target. So we can actually make predictions of how W relates to D looking at this graph, and we can actually figure out what the optimal signal to noise ratio is. So I haven't talked about the nervous system at all, and there's kind of a good reason for that. It's because if we want to build an internal model of this, we can do that in a number of ways. But we have to understand kind of what the kind of parameters of learning are, what the kind of parameters of processing are. And then we can add things in like a learning rate and also an internal model. But we won't get into that in this set of slides in this talk. We're going to kind of go in a little bit more into detail on this equation. So we have our bandwidth, which is the index of difficulty. It's basically the number of bits it takes to be accurate in hitting a target. And then how much information is in that act. And then we have another parameter H, which is taking this ID in the top equation and dividing that over time. So now we have our movement time. And of course, like I said, your time, this is a time-constrained process. So when I make a targeted movement or a movement towards a target, it's a ballistic movement. But if I have more time to think about that ballistic movement, or if I make a very slow ballistic movement towards a target, I can hit it much more accurately than if I have to do it very quickly. So, if you can think about like if you have to, say for example, if you're startled and you have to throw a dart at the board, versus if you have time to aim and throw your dart at the board, then the time becomes a limiting factor on your bandwidth and ultimately on your accuracy. Another interesting part of this, of course, is that learning rate can be used to normalize this measurement. So if you learn these movements, if you're very good at darts, say, if you're an expert versus a novice, your movement time doesn't need to be, it's not as constraining as if you were, a novice. So an expert might require less movement time as a constraint versus a novice. So, for an expert, I might get H for much lower values of T than for a novice. And we can put in that learning rate and discount the time, but we won't do that here. So H is really our throughput. ID is simply our measure of information in bits. That's sort of a description of throughput, but the true description of throughput is normalizing that by t. And then maybe even by learning rate if that's something that you have available. So we can actually break down our index of difficulty into two parts. So we can look at the index of difficulty, which is summarized by the equation we've shown previously for that. And then, of course, we take d, which is the distance to target, so it's a component of ID. And of course, we're taking index of difficulty over a time interval, and we're getting our bandwidth. So let's look at the function that we get for ID versus distance to target. We see that there's this linear phase and throughout most of the distance. For very small distances, however, we get this sublinear component, which goes to -5 or more of ID, and that's just the way that was normalized. So this red box shows the regime here of superlinearity. And we can also think of throughput, aside from being h, as being sort of a derivative of ID. And in that case, the throughput is highest for values of longer time duration and longer distance. So this is how we interpret this graph. It's longer time duration, longer distance. That translates into a high signal for long time intervals. So in other words, if you have a lot of time to think about moving to your target, you have high signal as well because you have time to plan, the signal is processed more thoroughly, and you can make the movement and hence get this superlinearity. So if we revisit our equations for index of difficulty, which is the information, and bandwidth, which is the h, we end up with a summary of some of the other things we can plug into this. So we take our bandwidth and we multiply it by a couple of factors that we've talked about but haven't added them into the equations. And we end up with h prime, or the bandwidth prime, which involves all these other parts. So the first thing we have is learning rate, and that's small alpha, and that refers to the learning rate of the model that we use. And this is just specifying learning. The second part is the internal model. So we can differentiate between the learning rate of the internal model and the sensory transformation potential of the internal model, which I've used the notation for a transposed matrix just to, we can use any kind of equations, what we want in this, but I'm just using shorthand for now. So there are two parts to the internal model. Technically, there's the learning rate, but also the sensory transformation, which is important. And we could also have maybe like a planning rate as well, but that's maybe incorporated into the learning rate or some combination of these two. And then finally, we have the kinematic chain, which is a summary of embodiment. And we'll get into this in the next slide. This is a summary of the degrees of freedom of your effector, or in this case, your arm that's making the movement. And summing over all those degrees of freedom for each degree and its current state. We'll get into that in the next slide. That's the kinematic chain, which is also a summary of embodiment. So we're actually going to talk a little bit about embodiment here in terms of what the operator, the agent is doing. And there are a lot of ways that we can generate movement throughput. So Fitts law is used as a theoretical tool. You can look at mechanical systems, you can look at, biomechanical systems, and you can basically describe those movements, not just in terms of like the target distance and the target size, but you can also look at it in terms of the actual effector or the actual anatomy of the system making the movement. So, we have like sort of a first order system, which is a catapult. If we put an object in a catapult, we can flick it, and it doesn't have a brain, it just has like a simple mechanism for generating a ballistic movement. We have something in human arms, in any kind of arm really, called a kinetic chain. So the kinetic chain is where you have the system of links and joints, and they have different degrees of freedom. You can see the different degrees of freedom here. You have a shoulder, elbow, wrist, and they all articulate in different ways. And then the effector has different angular configurations which generate angular momentum, and that can play a role in generating that ballistic movement as well as the internal model. But the kinetic chain also suggests that if you start a movement at your shoulder, the movement amplifies as you get down to your wrist. So when you make a movement at the shoulder, the movement at the wrist has a higher sort of error rate or higher sort of higher frequency output. So, these are things that your nervous system has to account for. These are things that the movement system has to account for. It's very different than a catapult, I guess is the point. And then finally, we have the muscular hydrostat, which is something we find in octopus. And the muscular hydrostat are a series of little muscle ganglia that are joined together. And they all articulate independently, kind of like the kinetic chain example of the human arm, where you have different degrees of freedom at different joints. But we have a lot of different joints in the muscular hydrostat. They can be coordinated or they can move independently. And so we have many, many higher degrees of freedom, and actually even more of a kinetic chain than the human arm. And one of the consequences of this is that the manipulability of the muscular hydrostat is much higher than the human arm, or especially the catapult, and it allows for very controlled movements and other things like that. So when we think about this Fitts law equation, we have to think about this in terms of the system generating the motion as well. We have to think about the degrees of freedom available for the motion. We have to think about how much control you have in that effector, and so forth. And so another thing that is involved in generating movement throughput is, of course, this aspect of how is the space explored, how is the space parsed, and how is the movement generated. As I said, you have these ballistic movements, which are good for linear movements to a target, but you also have things like random walks and biased random walks. And these are movement modes that maybe involve multiple targets, or they involve planning through a space, thinking, what is the best movement to that spot? And so, we can have, say, for example, an internal model that models the environment as maybe like a random walk, or we could have a model that models it as a least squares distance, or we could have a system that models it as a biased random walk. And this happens a lot of times in single cell organisms that do chemotaxis, where they move towards across the chemical gradient towards the highest concentration of that chemical, and it constrains their effort to a target. They don't need to go through all of the planning of a random walk. They also don't just leave it at the least squares aspect. They actually follow something, and it's kind of in between those two. So there are a lot of ways that the internal model can figure out, kind of how to get to the target, what's the most efficient path to the target, and so forth. This leads us to something, we can go back to entropy, and we think about, what's going on in the brain, but also in the body. And we're kind of all over the place with this. We might get all over the place with this, but we can ask the question, how much entropy is expended to gain a certain amount of energy? So if in terms of gaining a certain amount of energy, we can flip that around and also say, how much entropy is expended to gain a certain amount of information or information throughput? And so, we think about thermodynamic entropy, but we can also think about information entropy in the same or a similar way. And so, one thing we can do is think about the world, the visual world, or maybe like the world of haptic perception or whatever, the environment. And we can think about building this as sort of a network of sites or targets. And we can think about how to calculate the sort of the potential as well as the actual thing we want. So we can think about this in terms of average path length, which is the path traveled by the end effector. And this is defined as the distance from a location to a destination. We could assume a discrete set of points extending from the body to the edge of the perception action volume. We'll look at that in the next part of this series. But we can think about this as a spatial network. So this is one example where we have a human sitting in a chair or seated, and then this volume around their upper body, the torso, the head, and this is their reachable volume. This is the volume which they're doing these sensory motor interactions. They're looking at objects, they're grabbing towards them, they're moving their end effector or their arm towards the target. So this can be defined as a volume. So we can think about this volume as being a place that you can plan different movements, that you have different configurations that you can take, and what are the most efficient ones. And so then we can think about this in terms of our end effector or our arm being able to visit locations in this volume. The edge of the volume relative to the individual is the end goal state. So they have to pick some end goal state along the surface of this manifold, and they reach towards it, and they have to, basically figure out how to do that. And so then the target locations that we take form a manifold that describes our whole environmental stimuli. So that's all I have for this part. Thank you for joining me, and see you later in part 4.